past few decades, emerging evidence has proved inconsistent with the traditional models of a large, melt-dominated magma chamber. So geoscientists have set to re-evaluating models of magma storage. Understanding the pre-eruptive assembly of magma prior to large eruptions is key to understanding the eruption triggers and informs our ability to monitor and predict large eruptions. In order to do this, I have examined the petrology and geochemistry of cumulate nodules erupted and incorporated into the ignimbrites of 3 early Pleistocene eruptions on Tenerife, the Gaviotas, the Morteros and the San Juan. The cumulates consist of a diverse crystal assemblage, with between 0 and 77% interstitial melt. Many samples contain greater than 10% of minor phases, such as apatite and magnetite. The cumulates represent live material that was incompletely solidified and became frozen into a nodule upon eruption. The cumulates were classified as displayed in Figure 1 and revealed 3 domains of the magma chamber: ultramafic cumulates, taken to represent the base of the reservoir, mafic gabbroic cumulates, and felsic cumulates. There is a diverse range of texture and variability across the cumulates. Dissolution sieve textures are prevalent across a wide range of cumulate crystals, sometimes as extreme as leaving skeletal plagioclase. Zoning patterns including oscillatory, sector, normal and reverse zoning, in addition to distinct green-coloured cores, are visible in clinopyroxene phenocrysts. Poikilotic and ophitic textures are observed in some cumulates, highlighting their complex histories. Zoning patterns on compositionally distinct crystal cores of minerals have previously been interpreted as crystallization from multiple distinct batches of magma. In addition, the dissolution sieve textures are commonly interpreted as indicating the crystal is in deep disequilibrium with the interstitial liquid, and therefore unlikely crystallized from this liquid composition. The prevalence of these features across the cumulates make plain that there have been multiple phases of melt infiltration and multiple liquid compositions present throughout the development of the magma reservoir system. The interstitial melt of 19 cumulate samples was separated and analysed for trace and major elements using ICP-MS. Tenerife magmas plot along the alkaline series, from basanite to phonolite. The interstitial melts analysed range from tephrites and basanites to basalts and trachybasalts, with the older Gaviotas formation being more silica poor and the Morteros formation having a higher alkali content. However, the silica content of the interstitial melts is poorly constrained, as it is not directly measurable using ICP-MS. The silica content was calculated using this equation, which neglects the presence of water or volatiles, likely resulting in errors of 4 to 5 weight% silica. This is likely the cause of the anomalously low silica we see in the Gaviotas formation. The relationship between cumulate crystals and the interstitial melt material is examined in Figure 3b, inspecting whether the more primitive nodules, taken to have a higher percentage abundance of clinopyroxene, have more primitive liquids with a higher magnesium number. The more primitive nodules do not appear to have more primitive interstitial liquids at the time of eruption, taken to indicate that the crystals are not directly related to the interstitial liquid they have been erupted with. This is consistent with the extensive dissolution sieve textures observed across many phenocrysts. This could indicate that the interstitial melt was the carrier liquid of the nodules. The rare earth element patterns of the interstitial melts are displayed in Figure 4. Each formation has a broadly similar pattern, enriched in light rare earth elements compared to heavy rare earth elements. In addition, the interstitial melts have comparable rare earth element patterns when split into cumulate type. The comparable rare earth element patterns between these cumulate types does not concur with the 3 domains, ultramafic, mafic gabbroic and felsic, of the magma reservoir that are suggested by the cumulate petrology. One sample from the Gaviotas eruption was noted to have interesting and anomalous intercumulus glass ground mass, with the distinct colour changes and swirling patterns within the glass. Analysis of this glass was carried out using an SEM, taking the average composition of 2 regions within each of the 4 sites A, B, C and D, shown in Figure 6b. Sites A, B and C all plot in the phonolite field. However, Site D, the darker glass, plots in the trachyite field. Comparison with the interstitial melt material of the gaviotas, calculated from the major element data, shows that these compositions lie on a mixing line, with the Site D trachyite composition plotting slightly below the line and towards the interstitial melts. However, as the interstitial melt silica is poorly constrained, it is better to examine magma mixing using other major element ratios. A mixing line between the averages of the basanite and phonolite groups has been plotted, with all sites lying on or very close to the line, with Site D measurements plotting along the line towards the gaviotas interstitial melts. As the Site D trachyites plot along a mixing line with the interstitial melts, they are therefore interpreted as the result of mixing of a phonolite and basanite composition. The mixing of magmas has been observed in Tenerife by other authors and has been suggested as a trigger for eruptions. Phonolitic compositions are usually observed as erupted pumice across the Bandas del Sur in Tenerife. Therefore, quenched uninflated phonolitic glass that did not explode upon eruption is unusual. This could indicate that the phonolitic liquid was trapped in an isolated melt pocket or a small magma chamber, hence explaining why it quenched as an unexpanded liquid. This sample provides a unique pre-eruption snapshot of the mixing of magmas and disaggregated cumulate crystals. As the mixing of the trachyite and phonolite compositions is clearly visible in the colour of the glass, this mixing must have occurred very close to the eruption in order for the compositions to have not homogenized. So what does this data mean for magma storage beneath Tenerife? Figure 8 provides a suggestive model of the magma reservoir beneath Tenerife, based on the data collected in this work and the data collected and modelled by other authors. This study supports the presence of a lower crustal basanite mush system and an upper crustal poorly connected phonolite reservoir. The cumulate crystals record diverse and varied histories in multiple liquid compositions, with great heterogeneity throughout the reservoir. As the interstitial melt doesn't concur with the three domains suggested by the cumulate petrology, it likely represents the carrier liquid of the nodules and may be mixed and hybridized with other compositions encountered throughout the mush system as it was disaggregated. So, to conclude, the data supports an upper phonolite reservoir and a lower crustal basanite mush system, with the mixing of these reservoirs occurring closely prior to the eruption, as seen in the intercumulus glass. The interstitial melt likely represents the carrier liquid of the nodules and may be mixed and hybridized with other compositions encountered, as the mush disaggregated. This work has wider implications for the structure of reservoir systems beneath low-flux ocean island volcanism and the explosive periodic volcanism on Tenerife. Thank you for listening.